In this lesson, we're going to talk about exponential functions. So first, what's an exponential? A function has a constant percent increase, which is known as a growth, or a constant percent decrease, known as decay. So we've seen linear functions that grow at a consistent rate, like constantly increase by the same amount. Exponential functions grow at percent rate, so they grow extremely fast if it's a growth, or die extremely fast if it's a decay. Right, so that's the difference between an exponential and a linear. This is a linear function. It's a line. And then these are exponential functions. They grow really fast and they decay really fast. So what do these equations look like? Well, in general form, they look like this. Y equals a, b to the x. There's an exponential there, hence an exponential function. Now let's talk about how we break this down. So x and y are the xy points, coordinate points. A is the initial amount. So a is our initial. Kind of like in a slope-intercept form, it would be like the b, right? The y-intercept. So this is our initial amount. It's not a y-intercept, it's initial amount though. And then our b is our constant ratio. So that's the amount you're multiplying by each time. That's also what makes it different than a linear function, right? A linear function, you're adding the same amount each time. In an exponential function, you're multiplying by the same amount each time. That b is also known as a growth or decay factor. So if that b is greater than 1, it's known as a growth factor. And if that b is less than 1, it's known as a decay factor. So this graph here, that's a growth. So the b here was greater than 1. The b here was less than 1. Right, we're getting smaller. We're multiplying by something less than 1. So it's smaller every time. And an asymptote, we'll see these on graphs. That's a line you get close, but you cannot cross. That's all asymptote is, right? It's an asymptote is a line that a graph of function approaches but never reaches. So when you see an asymptote, it's a line you can never go past. It's a little more horizontal, is a little more complicated than that, but in general, asymptote is a line you're not going to go. You're going to get close to, but never pass. Okay, let's graph our first exponential function, and we're going to graph it like we graph everything else. We're going to make a table, right? So how you calculate that's how we do it. So y equals 3x, a table. We have an x value, a y value, and then we're going to have our point. We're just going to plot these points. So we'll start with the standard, -2, -1, 0, 1, 2. And the way this works is if -2 is going to subset in for our x, so we're going to get 3 to the -2. We talked about this before. What a negative power does is it flips it, so it becomes 1 over 3 squared, which is 1 over 9. So our point would be -2 and 1 over 9. Now we're going to do a lot of estimating here. But -2 and 1 over 9 will be like a very small number right there. Right? Much less than 1, close to 0, around there. And we keep on going. 3 to the -1. Remember, negative power just flips it, so that becomes 1 over 3. And that's our point. -1 and 1 over 3. So it's a little higher up. Next point, 0. 3 to 0. Well, anything to 0 power is 1, so we get the point 0, 1. Like that. And let's plug in 1. 3 to the first. That's just 3. So 1 and 3 is our next point. Right there. And then you can start seeing it really fly. 3 squared is 9. 3 times 3. So 9. So I get the point 2, 9. So 2 all the way up to 9. I didn't even make that many points yet. Right? If I went another time, 3 cubed is 3 times 3 times 3, which is 27. I'll be off the map. Right? Exponentials grow fast. And we're never going to cross. We'll talk about this more in a second. There's an asymptote right here at y equals 0. We're never going to cross that. And our graph looks something like this. Should be closer to the 0. So like that. And that's our exponential graph. Now I skipped some questions. Let's answer these. So keep in mind we have an exponential graph, right? So that equals y equals a to bx. It wants to identify the a value, the b value, the asymptote, the domain, and the range. Let's start with the a and the b value. So remember right here, b is the easiest one to tell. B has an exponent. So our b value is 3. The a value is the number in front of the 3, which in this case we don't have one. So remember, if it's not there, it's a 1. So A is 1 in this case. The asymptote, we'll talk about this in a second, but asymptote in this case is y equals 0. That's the line we cannot cross. The domain, our left goes from negative infinity to positive infinity. Right, left to right. And our range going low to high. So lowest is 0, highest is infinity. All parentheses because we can't hit the actual values. But that's our first exponential function. Let's do another one. So we're going to do some right here. So same idea. We want to graph it. So we're going to make a table. X, Y, and our points. We're going to use the exact same points. We're in IM1, so we'll just use the exact same points every single time. Our starting set there. So here's my equation. I guess before we do that, let's answer some of the things, right? They want us to point out what A and B are. So now we actually have an A in this case. Our A is 3, which is our initial value. And our B, our growth rate, is 2, right? So we're basically growing by 2 every single time, by a factor of 2 every single time. And our initial value is 3. That's what's going on here. So let's plug it in. So when x is -2, I get 3 times 2 to the -2. Remember, the negative power flips, so I get 3 times 1 over 2 squared, which is 4. So I get 3 over 4. So my point is -2 and 3 over 4. Next one, 3 times 2 to the -1. So that's 3 times 1 over 2, or 3 halves. -1 and 3 halves. Here we get to a fun one. 3 times 2 to the 0. And remember, the 0 is only for the 2, not for the 3, right? That's 1. And 2 to the 0 power is 1. So I get 3 times 1, which is 3. So 0, 3. 3 times 2 to the first. That's 3 times 2, which is 6. So 1, 6. And then 3 times 2 squared. That's 3 times 2 is times 4. 3 times 2 times 2 is 4. So I get 12. So you get 2 and 12. And look at all the y values. They're to mean times by 2, right? So 3 times 2 is 6. 6 times 2 is 12. Right? They're doubling every single time because that's what our growth rate is, 2. Anyway, if we're gonna plot this, I have -2 and 3/4, so close to 1. I have -1 and 3/2, a little higher than 1. I have 0 and 3 up there. And I have 1 and 6 off my grid already. And I have 2 and 12, so it's way up there, right? Exponentials grow fast. So we get a graph. Asymptote is always going to be at 0 for now. When you get to higher math, it'll be someplace else. For now, it's always at 0. And then we have a graph looks like this. And it's always at 0 because our power can never be negative. No matter what power you put, it's never going to be negative. It just gets smaller and smaller. But that's what our graph looks like. Okay, so we did a couple growth ones. Let's do a decay one. So we're going to do the exact same thing here real quick. Right, so y equals ab to the x. Now again, I only have a b this time, so b equals 1/3. If you don't have an a, that a is 1. Let's make a table. Exact same thing we always do. X, y, and then our point. -2, -1, 0, 1, 2. Again, you can do more points, but those are the standards to get you a good picture in this class. So substituting -2. So 1/3 to -2. And remember, a negative power flips it, so this becomes 3 over 1 squared, which is just 9. So -2 and 9. 1/3 to the -1. Again, negative power just flips it, so 3. So -1 and 3. 1/3 to the 0 power. Anything to the 0 power is automatically 1. So 0, 1. 1/3 to the first power. That just keeps it the same. 1/3. So 1 and 1/3. And 1/3 squared. So that's 1/3 times 1/3. Should be 1 over 9. Or just 1 over 3 squared. So 9. So 2 and 1/9. So if I was going to plot this, something like that, we're actually starting -2's at 9. Because remember, this is a I'm ready to talk about it. This is a decay graph. Right? Anytime your b is less than 1, it's between 1 and 0, I should say, it's a decay graph. Anytime your b is greater than 1, like we had here, it's a growth. So now we're doing a decay graph. It's a different graph. So negative 2, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. I think that one's 9-ish. Negative 1, 3. So negative 1, 3. 0, 1. 1 and 1/3. So that's small. And then 2 and 1/9 even smaller. So our graph looks like this. Right? It's an exponential function that's dying really fast. Very important, do not go past the 0 line, because remember, we always have an asymptote at 0. So let's do domain range. Let's get out of the domain. Negative infinity to infinity, right? Left to right, farthest I go, arrow, negative infinity, farthest right I go, arrow, infinity. Range, starting at 0, we're going to infinity. Right? That's where asymptote is always at 0. This thing is the exact same one for this one. I forgot to do it here. But my domain would have been negative infinity to infinity. My range would have been 0 to infinity. Okay. Let's move past that. Now, can we tell if it's a growth or decay just by looking at the functions without graphing? Yes, we can. Remember, our generic function is y equals a b to the x. It's a growth if b is greater than 1. It's a decay if b is less than 1, between 0 and 1. If it's less than 1 generally. So look at the first one here. That's your b is less than 1. That's a decay. 5 is bigger than 1. That's a growth. 4. Trying to trick me here. That's a negative x. So remember, a negative power flips it. This is actually 12 to the 1 over 4x. That's a decay. Trying to get me. This one, 1/3, decay, less than 1. No trick there. 4.7, bigger than 1, growth. Right. Okay, there'll be more of the same. We're going to skip past those. Okay, let's write, given a table, let's write an exponential function. So we want to write it in this form. It's not as bad as it sounds. We have to remember what all these things mean, right? So A is the initial amount. Kind of like the y-intercept, not technically, but it is going to be when x equals 0. And then B is our growth rate. So it's what you multiply each time. Okay, so let's go to our first one here, right? So our initial amount, right there, that's my A. My A is 4. Now we want to find the growth rate. So what are we multiplying by each time? So 4 to 12, 12 to 36. If you're not sure, B always equals like the second term over the first term. 12 over 4, or 36 over 12, or 108 over 36, right? It's always the next term over the first term, or the previous term. So in this case, I get 3. We're multiplying by 3 each time. So there's our equation, y equals 4, 3 to the x. That's how you write an exponential function. Find out where you're starting, that's your A, and then what you're multiplying by each time, that's your B. So this is an easy one, this is a growth. This was a little tougher. So my initial is still good. My A is 81, easy. But what are we multiplying by each time? Now in this case, it's actually smaller, so we're dividing, but our formula is always in multiplication form. So you have to figure out what the multiplication of this is. What do you multiply 81 by to get 54? If you're not sure, right, always put the next term over the first term. The second term over the first term, or the third over the second. It's a 54, by the way, it's ugly. 54 over 81. And then this we can reduce the divided both by 9. So 54 divided by 9 is 6. 81 divided by 9 is 9. And actually I could reduce that a little bit further, because I'm dividing both by 3. And you get 2 over 3. So that's what we're multiplying by each time, 2/3. And you could double check your work. If I multiply 54 by 2/3, you will get 36. So my equation here is going to be y equals A, which is 81, times B, 2/3 x. So this one's a decay, which makes sense. It's going down each time, right? This is like this, it's going down, it's decaying. While this one's a growth, it's going up each time. Right? And if I was going to do a couple more just to show you, right, do a little faster. My A is 7, and we are timing by 2 every single time. So this would be y equals 7, 2 to the x. This one, you might be going, oh, we're dividing by 2. You can't put in the divide sign, right? So if you're not sure what that is, just put the second over the first and reduce. The zeros cancel, I get 4 over 8. Divide them both by 4, and you get 1/2. So my a here would be 0. So I would equal 80 1/2 b x. Right, so again, your b is where you're multiplying by your sign. You know we're dividing by 2, you can't put divide by 2, you have to put in multiplication. So times it by 1/2. And then this last one here, let's compare a linear to an exponential. So which one's linear? Remember, a linear one is when you add the same thing amount. So we're going to add. Exponential is when you multiply by the same thing each time. So our first one here looks like we're adding 25. So this will be a linear function. And over here, we are multiplying by 3 every single time. So that's an exponential. To go a little further, I could write the equation for both of these, right? An exponential equation, y equals ab to the x. A is going to be 1. My b is going to be 3. In the linear function, we have more like y equals mx plus b. My y intercept is 100. And your slope, since it's kind of about ones, change in y is 25. The change in x is 1. So my slope would be 25. So that's a linear function. Keep in mind, it's right. You're adding the same thing each time. And that's an exponential function, multiplying by the same thing each time. And that's the video.